So we ended last time, I went through all this commotion about that if a function has if there's two functions and their Poisson bracket is 0, that means they're compatible, which in this 2 degree of freedom case, it meant that there was a 2-dimensional surface. It means there's a 2-dimensional surface along which each of these functions is a constant. And I gave this kind of simple drawing of, okay, on the level sets of G, that's preserved under the vector field given by the Hamiltonian vector field given by function f, and then also level sets of f, these black lines, black curves, are preserved under the vector field given by the Hamiltonian vector field of G. And kind of ended there. But one of the main results is the idea of a completely integrable Hamiltonian system. So let me mention that. And this is usually considered in the canonical Hamiltonian system context. So that's where you've got Q's and P's. It's kind of the usual way things go. I'm just trying to see if my picture shows up. I have no idea. My picture is showing up. Is it? Maybe? Okay. I want to pin this video. Okay, I mean, that looks okay to me. Hopefully it looks okay to you. All right. Yeah, completely integrable Hamiltonian system. So for an n degree of freedom, system, it is said to be completely integrable if there are n functions of the phase space in involution, which we all know what that means. So typically, the first function we'll just say is the Hamiltonian, because we know the Hamiltonian will have a Poisson bracket with itself that is 0. So let's make that the first function. But there's n-1 additional other functions where the Poisson bracket between any two of them is 0. And by a similar reasoning to what we ended with last time, this means all these have, we've got a 2n dimensional phase space. Each function has 2n-1 dimensional level sets. So these are very large dimensional surfaces or manifolds. But because there's this involution going on, all of these are compatible constants of motion, which means there are, okay, now we're in n degrees of freedom. There's actually there are n dimensional surfaces along which all of these functions remain constant. And they are, in fact, n tori. They're topologically n tori. So that's why I've gone on and on about tori. So you don't need to even know what these functions are. It works the other way too. If you know that there are topologically tori present, then there must be some functions, whether known or not, in involution, n functions for your n degree of freedom system. So what is an application of that? If you did problem 2, the numerical problem, then you may have done, not that one, you may have done a calculation. This is from an earlier homework from another student where he got the surfaces. So here's that Poincare section for, E equals 0.15. That one's not so interesting. It's maybe this one. This is for energy 0.2. And you see there's this kind of scattershot region, and that would be the chaotic region. There's also these things that look like level curves on the right and on the left. These are cross sections of tori. So we can see there's evidence, numerical evidence, that there are tori. And even though we might not know what the function is, maybe we'll never know, we know that there must be some function that if we had it, it would, its integral or its Poisson bracket with the Hamiltonian would be 0. So the Hamiltonian would be one function. This other unknown function is the other function. Those two are in involution for this 2 degree of freedom system, which means motion occurs along, at least in that region of phase space, along 2-dimensional surfaces, which it turns out they have to be tori. So there's a question.
So those functions do not have to be globally applicable?
No.
So does that mean that every, say, a center manifold of some like equilibrium point or something like that must have a corresponding constant that is locally applicable?
I mean, locally, you could describe any surface analytically, locally. So
is there a local constant of motion, I guess is my question, like near and for any center manifold or something like that? Or would that just be a consequence of the fact that you can describe any surface analytically?
I think that would just be a consequence. You could describe any surface analytically. Plus, a center manifold could range across many different energies. So you might be talking about the center manifold intersecting a certain energy surface.
I see.
So the center manifold restricted to a certain energy, yeah, you can get that locally, analytically.
Okay.
So this result is kind of what gives rise to the action angle variable situation. It means that if numerically you see evidence that there is tori, then you could, at least in that region, describe the motion in terms of action angle variables. There may not be global action angle variables, but at least in that region, it would make sense. So I guess it's worth noting you don't even need to know these functions. You don't need to know these functions, Fi. It's enough to know that they exist. So some system that is made up completely of tori is definitely completely integrable. Some systems like that boat system for homework problem 2, there are regions where it is completely integrable and then other regions where it is not. And that's why a system like that would be called near integrable. It probably has terms that create the chaos, and the chaos happens when you're far away from kind of these tori cores. So that's kind of interesting. You can also have completely integrable systems defined for non-canonical Hamiltonian systems. So here I said this is considered for the canonical Hamiltonian system context, but you could have a non-canonical. So I guess we could say the notion of completely integrable also extends into the non-canonical Hamiltonian setting. I mean, there are some caveats there. The notion extends, but it's not going to be necessarily n tori, because we don't have n degrees of freedom anymore. The whole idea of degrees of freedom is definitely tied to the canonical Hamiltonian approach of there are Q's and there are P's. But for something like Euler's rigid body equations, remember that was a 3-dimensional system. But we could treat it as a non-canonical Hamiltonian system, and there were 2 integrals. I guess there it's just F1 and F2. One was the energy, and one was the magnitude of the angular momentum. And they were in involution, which there you would only have to do one calculation to show that. F1, let's say, was total energy, and F2 was the total angular momentum. Magnitude. And later, maybe not today, but there's PDEs that can be considered Hamiltonian, and some subset of those are in fact completely integrable, which means since a PDE is sort of like an infinite dimensional system, that means you have an infinite number of constants of motion. So an example that we'll probably talk about is there's a version of the shallow water equations called the Korteweg-de Vries or KdV equations. It's a PDE in one dimension that describes things like motion of water in a canal. And this is where solitons were first seen. But these shallow water equations can be, and this wasn't known originally, but they can be written in a Hamiltonian form. So which means they are Hamiltonian. And they can be shown to be completely integrable. So there are, and you can even explicitly calculate these constants of motion. So it's a countable infinity of constants of motion, which is kind of interesting. I think it's more interesting rather than something very important that'll be useful. Because as far as I know, they're like, that's the only PDE that's completely integrable. So there aren't, it's not like they're widely known. There are many, but this one definitely is. And it kind of, you can, because you're able to cast it in the Hamiltonian setting, you're able to even ask that question. Otherwise, people wouldn't even think to ask that. All right. Some other things I wanted to say about the Poisson bracket. Today, we're going to talk about, other than this, how the Poisson bracket is preserved under canonical transformations when we're talking about canonical Hamiltonian systems, and how you can even use this to find canonical transformations. And then I'll say something about time-dependent functions of the Poisson bracket, and then also using the Poisson bracket to do series expansions. And we'll see where that takes us. But this was something I kind of wanted to finish up from last time. I didn't get to it. So if you didn't answer that problem right on problem 1, you know, no biggie. But I guess we could do this kind of diagram. Things that are in involution, right? So if you're able to demonstrate that there's all these non-trivial functions, that their Poisson bracket with each other is 0, then that means there are n tori in the system, which definitely means that there is an action angle description for the system. And it's completely integrable. So I think all of these arrows are like implications going both ways. So if there are n tori in the system, then that means there are some functions in involution, even if you don't know them. It's completely integrable and so on. All right. What else? Canonical Poisson bracket. Sometimes I get to look at myself in this dune sea, and it's exciting.
Dr. Ross, quick question.
Yeah.
When you say that the Fi and Fj are non-trivial, to be clear, what you're saying is that they are not dependent on each other?
They're not, well, and they're also not constants. Like if I did F1 is 6, that's trivial.
So like, you know, specifically in the homework where we saw that F3 was the Hamiltonian and then F1 and F2 were kind of those chunks. Were F1 to F3 in involution in that example, or no, because they were linearly dependent?
So in this case, F1 and F2 were in involution. But because F3 depended on F1 and F2, it was kind of trivial. So yeah, you should have found that F1 and F2, the Poisson bracket is 0. And I think F1 and F3 would have the Poisson bracket 0, but it doesn't really tell you anything.
Right, yes. Okay,
Yeah.
That answers my question. Thank you.
Okay. All right. So now, talk about the canonical Poisson bracket. That it is preserved under canonical transformations. So this means that if you've got a function f with g, and you calculated that Poisson bracket in, say, your original coordinates. So I'll put a little subscript q and p. Well, suppose you had done a canonical transformation to big Q and P, some other set of variables. Well, it doesn't change the value that you get from the Poisson bracket. You would calculate the same thing. So that's just a statement of this underlined statement above. The canonical Poisson bracket is preserved under canonical transformations. And how can we can actually use this? So this includes the fundamental Poisson brackets, if you remember what those were. Those were the Poisson brackets where a coordinate and its conjugate momentum, the Poisson bracket of those two, well, Qi with Pj is the Kronecker delta, meaning it's 0 if P is not the one conjugate to that Q, and then it's 1 if they are. And So the key takeaway here is that this is true for all canonical coordinates. Canonical sets of coordinates. So we can use this preservation property to find new canonical transformations. How's that? Let me give a 1 degree of freedom example. So, just one single Q and a single P, we want to transform to big Q and P, some new set. And we know that big Q with P, whatever this new set is, especially in the original variables, by this fundamental Poisson bracket property, this has to equal 1. But this also has to equal 1 if we were to do big Q, which, right, is a function of little q and little p, and big P, which is a function of little q and little p, do the Poisson bracket in terms of the little coordinates, the original coordinates. And just to give you a reference, if you wanted to see where this is, it's in section 6.3 of Hand and Finch, where they describe this. So how do we use this? First, let's just write big Q in terms of little q, just to get this going. So let's say I want, for whatever reason, maybe I'm trying to make the Hamiltonian in the new coordinates look really nice. So it would be convenient if the new coordinate capital Q is actually little q squared. Okay, so if that's the new coordinate, what is the conjugate momentum to that coordinate? It's not obvious, but we can calculate the Poisson bracket. And here, this will be the subscript actually doesn't really matter, but I'll keep it in there. So this is Q squared with some unknown function of little q and p that I call capital P, whose Poisson bracket equals 1. So you can try some things and see what works. So here's something that we can try, and you could write out what the formula is for this, like partial P, partial Q, partial P, and go from there. I just want to kind of demonstrate this is actually it. This is the conjugate momentum, little p over 2q. So if we put that in here and then write the Poisson bracket. Now here we can use properties of the Poisson bracket. I think this was one of those, remember, 5 properties? This is 1 over 2q times q squared p, Poisson bracket, plus p, Poisson bracket of q squared with 1 over 2q. This thing on the right-hand side is going to boil down eventually into something that's multiplying the Poisson bracket of q with q. And the Poisson bracket of anything with itself is 0. So this is going to end up, you do some algebra, do some Lie algebra, it becomes 0. And then what are we left with here? If we work out the Poisson bracket for what's left, we're going to get, this is, well, 1 over 2q is out in front already. We'll get 2q, q with p. These things cancel. This q with p equals 1, so you get 1. So even though it's not wasn't obvious. So QP, the original QP, to a new capital Q, capital P, which equals little q squared and P over 2Q. That is a canonical transformation. And I think someone has asked me in the past, can you get a canonical transformation like this from a generating function? I think the answer is yes, but I don't really know for sure. I think the answer is yes, any canonical transformation comes from a generating function, but I'm not 100% on that. And maybe the answer is out there. I've noticed a good way for getting answers for things. You go onto ResearchGate and you can ask a question. And then like somebody has it tagged to just look for things related to Hamiltonian, and they just love to answer. So you could ask, hey, does everything come from canonical transformation? Somebody's got an answer out there. Especially, I asked a question a few years ago when ResearchGate wasn't as popular, but now it is. I asked a question. I asked something. Well, you could look it up if you want. But it says I have stopped sharing my screen. Okay, I don't think I have. Maybe I have. Let me share again. Maybe my network connection is getting weird. Okay, now I see my stuff again. All right. So I wanted to mention that Poisson brackets are conserved under canonical transformations. I guess it might be worth noting here, canonical transformations are definitely tied to being a canonical Hamiltonian system. For non-canonical Hamiltonian systems, I don't know if there's a category of transformations that preserves the Hamiltonian structure, like a non-canonical transformation. I don't know. The only context I know them in is canonical Hamiltonian systems. There is a way to transform from certain canonical to non-canonical Hamiltonian systems, but that's separate. These words are too big. It's too much of a mouthful to say them. Okay, I wanted to mention time-dependent functions and the Poisson bracket. Because I feel like I give short shrift sometimes to, right? There's f dot. If you're looking at how a scalar function evolves in time, you would look at f with h. And then we usually leave out the possibility that f might explicitly depend on time, which, you know, if that's the case, then keep that in there. So this partial f partial t is sometimes non-trivial. Okay, so let's look at an example. I like to do this by way of an example. So let's just suppose we have a free particle. That means there's no forces on it. Free particle in 1 degree of freedom. So that means there's Q and then the conjugate P. So just think of a particle, it's just kind of moving in one direction. It's got an initial momentum and there's nothing to change that momentum. There's no forces. So the Hamiltonian for this is just the kinetic energy written in terms of the momentum. And then we will define a time-dependent function of the, well, explicitly time-dependent. So it's a function of Q and P and time. And it is just Q minus P over M times T. And so my claim is that this time-dependent function is a constant of motion. Which means capital F dot equals 0. So capital F dot is Poisson bracket of F with H plus partial F partial T. Okay. Of those two terms, partial F partial T is a lot easier to calculate. So let's just do that. Partial F partial T is minus P over M. And then we do the Poisson, calculate the Poisson bracket of F with H. Okay, what is this? Q minus P over MT with 1 over 2M P squared. And now you could use some properties of the Poisson bracket. This gets split into two, kind of like by the addition property. This is Q 1 over 2M P squared minus P over MT, Poisson bracket with 1 over 2M P squared. And now the dependence on phase-space variables over here on this second term, it's just dependence on P. There's no Q. So this also is going to eventually, it's going to be a bunch of things times Poisson bracket of P with P. And Poisson bracket of P with P, it's a fundamental Poisson bracket, which will give us 0. Whereas this other thing has Q in one of the slots and P in the other. So something else will go on there. And kind of by a similar approach from before. So you could bring out the constant 1 over 2M, then there'll be a 2P, and then Q with P. And that's a fundamental Poisson bracket, which equals 1. So we get, what do we get? P over M. So notice F dot, which is P over M minus P over M equals 0. Now, we haven't learned anything earth-shattering because we knew this from Newtonian mechanics. We just showed it in a new way. So from Newtonian mechanics, we could have said, well, the position along that one dimension at any time t is the initial position plus the velocity, which is p over m times t. I guess that's the initial momentum, but we know the momentum's not changing. So F, Q, P, T equal to Q at the current time minus P over M times time. And so this just equals Q0, which is the initial position, which is, you could think of, it's not a variable, it's a parameter. It's something that's constant. So obviously F, capital F equaling a constant isn't going to change in time. If you want some, if it wasn't obvious to you that P isn't changing the time, then you could do this calculation. This is just writing the equation of motion for P, but in the Poisson bracket form, right? It's the Poisson bracket of P with H. And so this would be P. And then all we need to know is that H is only a function of P. It's not a function of Q. Therefore, this will eventually boil down to Poisson bracket of P with P. So we could skip all that and just go ahead and say it's 0. So the momentum at any time is the momentum originally. All right. You can just go nuts with Poisson bracket. You can do things like Taylor series expansions, but they're Poisson bracket series expansions. And the usefulness about this is it could be used for non-canonical Hamiltonians too. So I will mention those. So these are, yeah, go ahead.
A quick question about constants of motion. So if the constant of motion, the expression for the constant of motion is time dependent, just having the Poisson has t in it somewhere, just having the Poisson bracket with the Hamiltonian equal to 0 will not guarantee that it's a constant of the motion, because you also have to include that other term to be sure that it all cancels out, right?
Yes.
Okay.
Yeah. But often functions that we care about don't explicitly depend on time, but there could be some interesting ones that do, right? All right. So Poisson bracket series expansions, and this includes non-canonical Hamiltonians. It's also, I think this gets discussed in, I will provide these references. Section 9.6 of Goldstein, which is, if I hope I put it somewhere, I think I've got it. All right. So because I'm including non-canonical Hamiltonians, I won't do phase space in terms of Q and P. I will write it more generally as X. So let's suppose that we have some function, it's a function of the phase space, not time. I think you could include something later for time, but for now, no, we don't have time. All right, then we know that the way that f changes with time, f dot, so derivative of f with time, total derivative, is just the Poisson bracket of f with h. Okay. Well, maybe I wanted to know not just the first derivative, maybe I want to know the second derivative of f with time. So f dot dot. What is that? Well, that would be the Poisson bracket of f dot with h, which is f with h, you know, etc. for as many derivatives as you want. Okay. This lends itself to a series expansion in time t to describe the function f as it evolves in time. So to describe how f evolves in time, or elapsed time, we would have f0. Maybe I'll write this as sub-0. So this is at time t equals 0, plus t df dt, evaluated at time t equals 0, plus 1 over 2 factorial. And you know, I'm just writing the Taylor series expansion. It's literally just the Taylor series expansion. Plus dot, dot, dot. But now when you substitute in for these derivatives and you put in the Poisson bracket, then it becomes a Poisson bracket series expansion. So f with t is whatever f is at time 0 plus t Poisson bracket of f with h evaluated at time 0 plus t squared for 2 factorial f with h. So you get these embedded Poisson brackets 0, plus, and then the next one would have a Poisson bracket of a Poisson bracket of a Poisson bracket. And there is the possibility that this series will truncate at some order. So if, well, maybe I'll kind of highlight this. My screen's doing weird things. So if, this is hard to draw, but I'm trying to put in like an embedded Poisson bracket situation. If this series, if this equals 0, if there's n of these embedded Poisson brackets, we can say n or k. I don't want to confuse you thinking this is related to the degrees of freedom. Let's just say k. So if there's k of these, then the series truncates. As all the higher order terms would also be 0. So then you would have not just a series expansion, but an exact solution. I mean, it means that f is just a polynomial of order, what, k minus 1 in time. But we can give an example of this. This is one of Newton's favorites. Falling under uniform gravity. It is not one of mine. I do not like falling under uniform gravity. So here I'm going to define from some reference height, I'll define Q, just one direction aiming down. Here's the mass M, and gravity is headed down. So the Hamiltonian for this is kinetic plus potential. What did I write before? It's 1 over 2m times p squared. And then because we're measuring downward, plus potential energy due to gravity is actually minus mgq. So that's our Hamiltonian. And up here we said, oh, you know, what's the function f? Here, my function f is just q. I want to know what q is as a function of time. And I'm going to use this elaborate machinery of the Poisson bracket to do that. So let's first calculate the Poisson bracket of q with h at time 0. So q with h at time 0 is Poisson bracket of q, p squared over 2m. And I mean, I can already tell you the other, that's the Poisson bracket with the kinetic energy term. With the potential energy term, you could already pull out these constants, mg, and then it's q with q. So that's 0. And so you could have just skipped that step and said, ah, who needs it? And I think you could figure out, or we probably already did up above, q with p squared over 2m. What is that? That is it's just p over m, and we're evaluating this at time t equals 0. So the initial time, which means this is the initial momentum over m. Okay. Now, what if we do, that's the next term would be Q with H with H. So this is going to be, well, we've already figured out what Q with H is. And then at the very end, we evaluate it at time equals 0. So Q with H is P over M. P over M as a variable. So we're looking at that times 1 over 2M P squared minus MGQ. I can already tell you ahead of time, the Poisson bracket with this P squared part is going to be 0. So let's just skip that. It'll be, you know, some stuff times P with P. So that's 0. So let's save ourselves some trouble. And then over here, we get G. The M's cancel, and we're just left with minus G, P with Q. And so this is G, Q with P, right? If you reverse the order, you pick up a minus sign. And Q with P is a fundamental Poisson bracket that equals 1. So this equals just G. So evaluated at time 0 is still just the constant G. And then because we know that's a constant, any higher order term is going to be 0. So Poisson bracket of Poisson bracket of Poisson bracket Q, H, with H, with H. There's like embedded bracket things going on there. Okay, that will equal 0. So series truncates. And we get an exact solution. Which fortunately we all know ahead of time because we've solved how things fall under uniform gravity. But here was another way to show it. And so we've got this plus, right, Q with H, evaluated at time 0 times T plus 1/2 T squared, Q with H, evaluated at 0. And then that was it, the series just truncates. So this is Q0 plus initial momentum divided by M times T plus 1/2 T squared G. And so this is true. This example is it's from section 9.6 of Goldstein. If you wanted to see that again. All right, and you could do. There's a whole like subtopic of Poisson bracket expansions that we just don't have time for, nor the patience, I might say. I mean, it's kind of interesting theoretical stuff. That's good. Sometimes these Poisson bracket things get used for improving calculations or even helping with doing simulation. So there is a connection between these Poisson brackets and what are called leapfrog integrators. So I wanted to mention that topic too. This is related to discrete maps and leapfrog integrators. The term will make sense hopefully later. And I'll post some notes. There's a few places you can get this info. One of them was, it's just some notes I found on the web. Someone named Saha. But, you know, thank you, Saha, wherever you are. There's also McClellan and Quizbull. Or maybe it's McLaughlin, like the singer, Sarah McLaughlin. I don't know. They had a 2002 paper. and Sands, Serrano, and Calvo, that little numerical methods book for Hamiltonian systems, chapter 12. All right, so the idea, at least for a leapfrog in integrators, you want to solve for the motion. You're going to come up with a numerical method, solve for the motion of a system described by a Hamiltonian that this Hamiltonian is complicated to solve, let's say, but you can decompose this into the sum of two Hamiltonians. So H does equal HA plus HB, and each of these alone are easy to solve, or easier. So where HA and HB are, let's say, easier to solve by themselves, either analytically or numerically. So they're easy to solve by themselves, but not together. And when this gets used, and this does get used, like this gets used for doing molecular dynamics simulations that are important for drug discovery or design of materials. People actually use this. They don't look at the super simple examples that I will. They look at, you know, a million particle systems. But for example, a common Hamiltonian that shows up would be where one of the parts is just the kinetic energy. And like we know how to solve something that's just evolving under kinetic energy. It's that example up above. It's the free particle. Free particles just go in straight lines and don't do anything interesting. The other part of the Hamiltonian might be the potential energy. And it's not so obvious, okay, what is something evolving under only potential energy and not kinetic energy? Yeah, granted, I don't know. But it would be easier because HA depends only on P and HB depends only on Q. So there should be some simplification that goes on there. And this is where in decades past, people designed these things called leapfrog integrators. So what's the idea there? We can approximate the motion under the sum HA plus HB under that Hamiltonian for a time step, and I'll call this time step tau, by following a leapfrog algorithm. So in the children's game of leapfrog, it's like you jump over somebody. And in this case, if we're starting, I'll put the steps over here and then kind of illustrate it on the other side. If we have our initial point, we're here in Q and P space, and we want to know where we end up after a certain time under HA plus HB under this time step, and maybe we end up here. Okay. Then the first step is you evolve under just HA for half a time step. And let's say evolving under just HA takes you only in like one particular direction. So we evolve for half a time step, tau, under HA, and we get here. Then you evolve under just HB for a full time step. And I will just draw that as like some going in some other direction. Maybe it takes us here. So this is for a full time step under HB only. And then the final step is you evolve under just HA for half a time step again at this new location. So from this new location for half a time step, we'll end up pretty close. So let's say we'll end up here. There's some small error. That we're okay with. And this error actually grows with tau squared. So this is considered a, like a first order accurate integrator. And the leapfrogging is, right, you do HA, then HB, then HA, and it's somehow it gets you close to the true answer. If you do these three steps, in sequence, they amount to evolving for tau under the Hamiltonian, which is HA plus HB plus something else, plus tau squared over 12, and then some embedded Poisson bracket thing. So HA with HB is in there. HB plus, oh, I think I stopped broadcasting again. I don't know why that's happening. I am at a different location. I'm not in my usual home. So that might be what's going on. Thought I was gonna show it. Oh, there, okay, yeah, just took a while. HB plus 1/2 HA plus order tau to the 4th. So all of this part is sometimes called the Hamiltonian due to error.
Is that tau squared over 12?
Yeah. It's weird. And I'll provide the documentation for this. It's more that this is it's a strategy for doing like quick simulation of usually large order, large dimensional Hamiltonian systems. So when you do these three steps, you are exactly evolving under a certain Hamiltonian. That's not the original one you wanted. It's got this extra piece tacked on, but you notice that extra piece, if you use a small time step, tau, then tau squared is small. So that error part will be small. I guess I should show up here. We're following HA plus HB with tau. That would take us to some point, and we're kind of getting approximately there. You could also use this for theoretical investigations of certain systems. So if we tried this on a pendulum, which I'll show, then interesting things will happen. But you'll also notice, right, if we wanted even a more accurate term or a more accurate simulation, the leapfrog algorithm works really well when the Poisson bracket of HA with HB equals 0. Because then that goes away, and then that whole second order term goes away. And then you've got an even more accurate simulation, because the next term in this error part is tau to the 4th. So if we did have like an HA that depended only on the momentum and an HB that depends only on the positions, then this is gonna equal 0. Unless, well, okay, no, that's not true. It might equal 0. It might equal 0. I'm getting confused. Yeah, it might equal 0. If you can find an HA and an HB where it does equal 0 or is small, then you're good. You're good to go. Yeah.
Quick question.
Yeah.
Is the significance, you know, like why do we do it in these 3 steps where we do a half tau and then tau and HB and then another tau, instead of like doing like 4 steps, all of them half tau, or 2 steps, you know, 1 in HA direction and 1 in HB direction?
I don't know. There's a whole cottage industry of these kind of algorithms. Those references I give would be a good place to start, but I can't answer that. I think there's a family of them, and this is maybe the simplest of the family. It's like half, 1, half, and there might be others that are like go a quarter, a third, a quarter, and I think there's a whole hierarchy of them. This is just the simplest conceptually, and I don't know why it is, but you can check out those references. In fact, you might want to do your project on that. I'll talk more about the project next time. I wasn't going to talk about it today. I only have 10 minutes. But part of your final homework will be thinking of the project. But I'll say more about that next time.
How much faster is this algorithm than just integrating it normally?
I think it could be really fast, especially if you can. So yeah, that's a cheesy answer. You probably want something like 1,000, but it depends on details. Like if you can analytically do HA or HB, then yeah, that's a lot faster than numerically doing HA plus HB. So I think the answer is it depends. It's a significant enough speed up that it allows, at least for the like molecular dynamics simulations, it allows certain things to be simulated that could not be simulated within the time of the known universe. So that's significant. But it depends. Like molecular dynamicists are excited when they can simulate 10 to the negative 15th of a second. They're like, yay, because they're doing things that change a lot in that small time scale. So if you could do like a whole second, you'd get a Nobel Prize. Let me give an example of this because it leads to an interesting discrete map. So interesting example is the pendulum. It's always an interesting example. It's slightly more complicated than the simple harmonic oscillator, so it's fun. An even more interesting example would be like DNA, but we're not going to do that today. So I'm choosing mass equal to 1. So the Hamiltonian is just 1/2 p squared, and then some constant k times cosine q. And we'll call, whoa, what the, things are going crazy. So I'm writing, this is my H. I will divide this up into HA, and this other part, it depends on Q, into HB. And then let's take a step size. Things are non-dimensionalized here. So we're taking just a step size of tau equal to 1, which is pretty big. Then what we will end up with for an integrator, and I think the steps are in one of those references I gave. But you'll get Q, the overall map, will say that Q goes to Q plus P minus K sine Q, and P maps to P minus K sine K. Like, why do you mean maps to? Well, that's what integrators do. They take initial points and then map them to where you are after one time step. Here we've taken a large time step. Another way to write this would be in kind of a discrete form, right? I'm thinking of, you've got pairs of Qi, Pi, and here's this point, and then this takes you to some other point, Qi plus 1, Pi plus 1. Okay, what is Qi plus 1 equals Qi plus Pi minus K sine Qi. And Pi plus 1 equals Pi minus K sine Qi. You notice this is the same as this. So this is sometimes written in a different form. Sometimes written as X equals Q, Y equals P, Xi plus 1 equals Xi plus Yi plus 1, and Yi plus 1 equals Yi minus K sine Xi. And because Q is an angle, it's sort of understood that this is mod 2 pi. So I'll write the map this way. This 2D map is well known in the development of Hamiltonian systems. And it's so well known that they didn't even give it a name. They just called it the standard map. It's a map of X and Y to X and Y. And depending on what you choose for K, you can get different kinds of behavior. It has a single parameter K. Whose value determines the kinds of behavior possible. So in some sense, the standard map, it's sort of like a chaotic version of the pendulum that is easy to implement on a computer, because if you start with initial points and it just maps where those points go to. So this map, right? You've got kind of the XY plane, and also X is like an angle, so there's a mod 2 pi going on if you want. In fact, maybe I'll draw Y over here. Here's Y. Here's 0 and 2 pi. So mod 2 pi means if you get something that's over 2 pi, you actually go back to where you would have been if it was between 0 and 2 pi. That's mod. But this map, the standard map, shows all of the richness of Hamiltonian systems. I mean, it's simple to write. But shows all of the richness of Hamiltonian systems. And I think I can show that to you. Like be super easy to code up, but people have been looking at it for a long time. It's not here. And it's in a folder that I will add. I've got something called the standard map here. I first learned about it from this paper from 1992. A guy named James Meese, who worked on Hamiltonian systems, but he got to that through understanding motion of electrons in a cyclotron, which also led to the standard map. It's just a standard map where X and Y here are energy and time. So this is the standard map over here. He's written this K over 2 pi thing so that his standard map, X doesn't go from 0 to 2 pi, it goes from 0 to 1, but it's the same thing. He calls his K, he calls that function K. I wanted to show what some pictures of the standard map look like. So here's the standard map for a really small value of K. Maybe this will update. Yeah, so there it is. Small values of K lead to things that look like kind of KAM tori or tori. And as you increase K, you get additional islands and things showing up like on the right. Once you get to a large enough value of K, and people have kind of calculated what that is, you start getting these chaotic bands. So here is, it'll show up another value of K, more and more chaos. And this is a kind of interesting discussion of the kinds of phenomenology, if you wanted to look at this paper. A higher value of K, he's chosen a really precise number, so there must be significant about that. And the standard map shows fractal stuff. So here is, starting at the lower right, we just sort of, you see there's chaos and then these islands of what look like tori. If you zoom in on one of those tori, it's expanded here on the lower left, and it's got a bunch of interesting things around it. If you just keep zooming in, you just keep seeing the same structure on the finer and finer scale, which is the hallmark of a fractal. So this does show, the standard map shows this kind of fractal behavior. And here's just another one for just showing a bunch of chaotic bands and things. And he goes on and on and on. And then he revisited this guy Meese 25 years later in a paper where he like color coded things, because eventually journals learned how to put color in. So I don't know what these colors mean. I think these are individual trajectories. So like the red part doesn't seem to be showing up. I don't know if it froze. It's showing up on my screen. Yeah, there it is. The red is an individual trajectory. So it started with an initial red condition, and then the blue are also initial conditions. Yellow is another initial condition, and you see it like not mixing with the red. But these show, the standard map shows all this interesting behavior, and anyway, it kind of is interrelated to this idea of coming up with discrete maps that solve a Hamiltonian system and so on. But I'm going to end there, and then we'll pick up Thursday. Yeah, you have questions? I know it's after 4:45, but I'm open to questions.
Dr. Ross.
Yeah.
I was wondering, so when you get into one of those, when you start off in one of those areas of chaos, are all the different, is basically when if you're in chaos, does that mean basically you can go to any other place in the map? Or are there almost like at certain values, like bands of chaos, where if you're in that area, you can go anywhere in that area, but you can't go to other areas of chaos? Or is that not exactly?
It's that last one that you mentioned. If you're in that area of chaos, then you can reach really anything else in that area. So like this standard map example, anything that's in the red, you could start anywhere in the red, any initial condition in the red, and it will eventually approach all of the other initial conditions in the red arbitrarily close. And probably the same for the yellow and the blue. As long as it's chaotic, if it's chaotic and a connected set, then you can reach anywhere in there. That's what makes chaos interesting, but also dangerous.
Is there anything significant about there being those different areas of the chaos? Like how you can't, even though you're in it already, you can't get out? Go to other areas that are still just chaos?
I mean, it's called bounded chaos. It just means that chaos doesn't mean chaos doesn't mean absolute randomness, or you could be anywhere.
Yeah.
It's there are bounds to it, and there might be certain regions that you want to be in and kind of not go beyond that. Like some people have looked at the controlled standard map. Like, what if I applied control? Then you could, at certain spots, maybe jump from the red chaotic sea to the blue one. And maybe that would be important for the design of some piece of machinery. Is you want to kind of be in this chaotic region for a certain reason, and then you want to jump to another. You can do that.
Would that mean that the chaotic region is an invariant set, but not an invariant manifold?
Yeah, there's a sense in which it's an invariant set. It'd be like an invariant subset of your total space. Yeah.
Okay.